Hello and welcome to part 4 of this video playlist about the preparation of pyridines. This video is about the alkylation and vinylation of pyridines by substitution of hydrogen. Because pyridine is an electron-deficient heteroarene, Friedel-Crafts type alkylations, hydroxyalkylations or aminoalkylations do usually not work unless the starting pyridine contains electron-donating substituents. But there are a number of other ways to alkylate pyridines. One practical way is the nucleophilic addition of organometallic reagents, followed by oxidation. This strategy can also be used to introduce aryl or vinyl groups. With some metals, or at a higher temperature, the metal hydride may be eliminated spontaneously, but if a polar organometallic reagent was used, the intermediate dihydropyridines can often be isolated. Aromatization would then require an additional dehydrogenation step. Another strategy is treatment of a metallated pyridine with an electrophilic alkylating reagent or with an electron-deficient alkene. With some transition metals, even simple unactivated alkenes can be used as alkylating reagents. I'll show you now some specific examples of pyridine alkylations with carbon nucleophiles. Aliphatic organolithium compounds usually add to pyridine, and careful hydrolysis will usually yield dihydropyridines. But upon heating, the intermediate will eliminate lithium hydride and yield the alkylated pyridine directly, as shown here. With Grignard reagents, however, this reaction sequence does not work. To alkylate pyridines with organomagnesium or other less reactive organometallic reagents, activation with a Lewis acid can be helpful. Here, 3-chloropyridine was first complexed with boron trifluoride, and addition of ethyl magnesium chloride and lithium chloride gave a dihydropyridine. Dehydrogenation with tetrachlorobenzoquinone then yielded the alkylated pyridine with high regioselectivity and in high yield. This reaction sequence could even be applied successfully to ethyl nicotinate and 2-chloropyridine. Another more expensive reagent to activate pyridines is triflic anhydride. Here, interestingly, no enol triflate of the starting ketone, but a dihydropyridine was obtained in high yield. Aromatization was achieved by base-induced elimination of potassium trifluoromethane sulfinate. Examples have also been reported of the addition of alkyl palladium compounds to pyridines. Such organopalladium intermediates tend to fragment into palladium hydride and alkenes, but occasionally reaction with electrophiles can be faster, as in this example. Although only one equivalent of cyclohexyl iodide was used, 55% of cyclohexyl pyridines resulted. One intriguing reaction is the formation of 4-ethylpyridine from pyridine, acetic anhydride and iron. The mechanism has been investigated carefully, and some of the intermediates could be isolated and identified. This reaction probably proceeds by initial single electron reduction of N-acetylpyridinium acetate to a neutral radical. Addition of this radical to the pyridinium acetate, followed by reduction, gives a thermally labile intermediate, which fragments into pyridine and diacetyl dihydropyridine. Reduction of the 4-acetyl group with iron and then by intramolecular hydride migration yields, after hydrolysis, the ethylated pyridine. Most dihydropyridines are enamines and thus more nucleophilic than pyridines. Sometimes it is possible to alkylate dihydropyridines regioselectively, as in this example. Here, pyridine was first converted into acylated dihydropyridine and then alkylated with an aldehyde. Unfortunately, the overall yield was poor and the scope of suitable aldehydes low. A newer one-pot version of this alkylation strategy was based on the initial reduction of pyridine with a borane. Apparently, during reaction with the imine at 80 degrees Celsius, the borane was eliminated again and no additional oxidation step was required. Thus, only catalytic amounts of borane should have been sufficient. I'll show you now some examples of alkylations with alkyl radicals. Here, a rather electron-deficient pyridine was alkylated at position 4 with radicals generated by oxidation of aldehydes. Only isopropylation and ethylation gave reasonable yields, while methyl or phenyl radicals did not. These reactions proceeded by oxidation and decarbonylation of the aldehydes, followed by addition of the radicals to the pyridinium salt and oxidation. As discussed in part 3 of this playlist, also acyl radicals can add to pyridinium salts, and acylated pyridines will result as byproducts here. The success of this strategy depends on the relative rates of acyl radical decarbonylation and acyl radical addition to the pyridinium salt. Donor-substituted pyridines do not readily react with electron-rich radicals, but only with electron-deficient radicals. In this example, the electron-deficient cyanomethyl radical, generated by hydrogen abstraction from acetonitrile, alkylated 2-aminopyridine with high regioselectivity and inacceptable yield. Here, the electron-rich cyclohexyl radical added to a pyridinium salt under acidic reaction conditions. The radical was formed by oxidation of a boronic acid with oxygen. Unfortunately, a large excess of this expensive boronic acid was required. Highest yields and selectivities are usually achieved with secondary or tertiary sterically demanding radicals. Single electron oxidation of carboxylic acids gives oxygen-centered carboxyl radicals that immediately decarboxylate to alkyl radicals. These radicals may just dimerize, as in the Kolbe electrolysis, or add to electron-deficient alkenes or arenes. In this example, alanine or pyruvic acid were oxidized by silver nitrate to an aminoethyl or acetyl radical, which then mostly acetylated 4-cyanopyridine. A small fraction of acetyl radicals underwent decarbonylation to methyl radicals, causing the formation of a methylated byproduct. Like in the previous example, here the radical was generated by oxidation of a carboxylic acid. Again, quite a lot of silver nitrate was required. In this example, only 20% of silver nitrate was used and a preformed N-alkylpyridinium salt was the starting material. The final cyclohexylpyridine was obtained in acceptable yield. This example is particularly interesting because no silver was required. It seems that in DMSO, persulfate is powerful enough to bring about single electron abstraction from carboxylates. Again, as in most of these reactions, the yield was moderate, but at least no expensive reagents or catalysts were used. One way to vinylate pyridines is by treatment with an internal alkyne. Here, a bulky Lewis acid and cobalt catalysis were required to bring about this reaction. No examples with terminal alkynes were reported, though. Similarly, alkenes can alkylate pyridines in the presence of Lewis acids and some catalyst. The scandium complex shown here seems to be particularly suitable for such alkylations. Unlike in the previous example, however, only positions 2 and 6 were alkylated. This example showed an incredible time dependence, which certainly deserves closer scrutiny. This here is an example of nickel-catalyzed alkylation of 2-picoline with allylbenzene. Again, with a bulky Lewis acid co-catalyst and at a high temperature. Only position 4 of the pyridine ring was alkylated in high yield. Similarly, alkylation of 3-picoline with styrene could be catalyzed by cobalt and boranes. As shown here, alkylation occurred again mainly at position 4. This is an example of oxidative Heck vinylation of pyridine. Instead of using a halogenated pyridine as starting material, the parent pyridine was treated with butyl acrylate, palladium acetate and an excess of silver acetate as oxidant. Vinylation occurred mostly at position 2, but regioselectivity and yield were only moderate. I'll show you now some examples of the lithiation of pyridines followed by trapping of the intermediate with a carbon electrophile. Because butyllithium alkylates pyridine, some additives are required for the effective metallation of pyridine. You can find further examples in parts 2 and 3 of this playlist. Here, pyridine deprotonation at position 2 was achieved with a mixture of dimethylaminoethanol and butyllithium at low temperature. Reaction with aldehydes or other alkylating reagents mostly yielded the expected products. In the case of benzyl bromide, though, the main reaction was electrophilic bromination. Metallation of pyridine at position 2 could also be achieved with a mixture of boron trifluoride etherate and magnesium tetramethylpiperidide, as shown here. The intermediate Grignard reagent was trapped with an aldehyde. The resulting secondary alcohol was then alkylated with chloroethyl dimethylamine to obtain the antihistaminic carbinoxamine. Halogenated pyridines are particularly acidic, and deprotonation usually occurs ortho to the halogen. In this example, 4-chloropyridine was lithiated with an excess of LDA at -60°C and then alkylated with acetaldehyde. As with radical additions, the regioselectivity of pyridine metallation can be difficult to predict correctly. Although unsubstituted pyridine is often metallated at position 2, treatment of 3-chloropyridine with LDA followed by ethylation with ethyl iodide gave exclusively 3-chloro-4-ethylpyridine. N-butylnicotinamide could also be selectively metallated and alkylated at position 4, as shown here. Attempts of nucleophilic substitutions at secondary aliphatic bromides mostly cause elimination, and the attained yield here is actually quite impressive. Although butyllithium usually adds to pyridines, the THP ether of 3-hydroxypyridine was mostly lithiated by this reagent, without the need of any further additive. Alkoxy groups often enhance the rate of metallation of adjacent positions in arenes. In this case, first position 4 of the pyridine was metallated, and after thiolation with a disulfide, position 2 could be lithiated and alkylated. Here are some more, mostly recent examples, which you can also find in the description of this video. The next presentation is about the arylation of pyridines, including oxidative pyridine dimerizations and the electrophilic arylation by pyridines of electron-rich arenes. So long.